All right, welcome everyone. Happy Friday. I'm sad to announce my cough hasn't really gotten better, so I apologize in advance for coughing throughout this lesson. I'll try to stay away from all of you. Today we are finishing up chapter 15. So this is the last topic of chapter 15. In particular, right, the most looming administrative announcement is that we have a test next week, 6 days. So you should start thinking about, what your study schedule will look like. Hold some time in your calendar and whatnot for some test prep and all that sort of stuff. So today we'll finish up chapter 15 like I alluded to. Monday's class we'll do the 16.5 thing, which I think all things considered is a relatively nice section. So I hope that it shouldn't be too difficult. This is a section about divergence and curl. Then next Wednesday we'll have a review class, just like we had before the midterm and before our first online test. And then, of course, Thursday will be the test itself. So that's kind of the main administrative stuff that's coming up. Are there any questions really about anything before we transition and start talking about math for today? I guess let me bring up again here, even though I did it last time, I think, that in our folder here, that I have published a knowledge checklist, right? So one good thing I think you should do is go through all of these sections, see where you're strong and where you still need a little bit of work. And so you should read each one of these. And in particular, so like today's class, what you should be trying to get out of it is, well, you should be able to convert from Cartesian to spherical. Certainly do examples of that. Beyond this, of course, you should be able to convert the full integrals to the bounds and, of course, the integrand into spherical. We should be able to graph these things, and we'll get some practice again in the RZ half plane, just as we did in the pre-class video. And then lastly, in purple here, you should have a general idea of when it's a good idea to integrate using spherical coordinates. So even if a problem does not say, hey, use spherical integration, you should know that, of course, when you're inside of a sphere or part of a sphere, right, spherical integration is a good option, perhaps. So these are the things that we're hoping to take away from today's lesson. Beyond that, I do have the review sheet published for next Wednesday's class. You can print that off and take a look at it. And yeah, I think that's about it. All right, so one last chance. Any questions before we transition and start talking about 15.9? Okay, 15.9 it is. Excuse me. So again, we're talking about spherical integration. We first talked about spherical coordinates back in like chapter 13. There was this little awkward section, I guess, 13.9 is how I denoted it, which we brought up cylindrical and spherical. And so you already know a lot of the transformation equations. And what we need to do now is know how to integrate these. And so a little bit of a review and sketching in this RZ half plane is what we did first in the pre-class video. And this is the idea that if your surface does not rely on theta, you can kind of collapse your thetas. So instead of, right, theta rotates this thing around the z-axis. And so if you kind of collapse your thetas, you get this RZ half plane sort of deal. And this is nice because in general, I think we're all better at graphing in 2D than we are in 3D. And so if we can graph something in 2D and then from that get a 3D picture, I think that's to our advantage. And so we graph these things first in 2D, in particular in this RZ half plane. We did a couple examples of that. And then if you want to get your 3D picture, well, you just take this and you allow your thetas to run free. The way your thetas run is around the z-axis. So you take your picture here and you just rotate it around the z-axis. And this is what gives you your 3D picture. So we did this once with the cone and once with the sphere. Again, this doesn't work for every single surface out there. In particular, they can't rely on theta, but luckily that does constitute a decent percentage of our surfaces. So although this technique does not work 100% of the time, I would probably gauge it works on the order of 80 or 90% of the time. It works quite often. And so even though it's not a foolproof method, there's some complicated surfaces that you can encounter that do rely on theta. It does work quite a bit of the time. All right, next up, we calculate out the Jacobian. So this integration factor. We did all the work of the transformation and whatnot. And we found out that we're going to need this rho squared sine phi. So every time we switch from Cartesian into spherical, we're going to convert our equation. And then we're going to have this extra integration factor that's Jacobian. That's going to be our rho squared sine phi. By the way, you may remember from back in chapter 13 that rho sine phi is just r. So you can imagine that when you convert into cylindrical, you get this r. And then if you take that one step beyond and convert into spherical, right, you need r and you need rho. So this is r rho, or AK, if you put it all into spherical, the rho squared sine phi. And then the last thing we did was an example problem with this information. In this one, we found the average height of a point inside of the hemisphere. So that's the pre-class video in a nutshell. Any questions or any things that maybe I could spend another minute or two discussing before we go on and we do the new stuff for today? Yeah. That's true. So it's important to maybe recognize that because, right, if we do x squared plus y squared plus z squared is equal to rho squared, in RZ, right, this would be r squared plus z squared is equal to rho squared. So essentially, your rho squared is now a radius from the origin of your RZ half plane. So again, kind of when we did this one here, we plotted different phi values, and then rho was how many steps should we be taking away from the origin. So this is essentially your radius here in your RZ half plane. So in the RZ half plane, rho is how many steps you are away from your origin, and phi is your angle off of the positive z-axis. So that's what these things look like in the RZ half plane. But yeah, it is a bit peculiar that you don't have, in the RZ half plane, spherical doesn't have either r or z. So you have to know what these things look like in the RZ half plane. Excellent. Any other questions? Yeah.
Why the volume of the sphere is like higher?
So the question was, will we ever show some of these volume formulas, like the volume of a sphere is 4/3 pi r cubed? You certainly can. They're just not very interesting. They go very quickly in spherical integration. So I think maybe that would be a good problem that I could include in the future for some pre-class video. But I think if I did that in class or whatnot, you would feel that this is too easy, especially when you compare it to like the web work homeworks and quizzes and exams and stuff like this. But we certainly will see other volume problems. Okay, well, let's go ahead and transition here and start doing some new problems. So this one's very explicit to us. It says use spherical integration. So we don't have to decide. But still, as you read this problem, you know, thinking about on the final exam, when you have a lot of material, I also don't see a triple integral anywhere in this problem. So the first thing to realize is that it's asking for a volume. And volumes are a triple integral of 1. Now the next thing is, well, it says use spherical integration. And so we could go ahead and convert this. Probably don't even need to write this one if you don't want, but maybe here I will. So this is all like the low-hanging fruit, right? This is, you know, if this was a 10-point problem or something like this, maybe this is worth 1 or 2 points of partial credit. So definitely worthwhile, even if you don't know how to do anything with the bounds, to at least write this part down. You have shown that you know that volume is the triple integral of 1, and you've successfully converted And remember the Jacobian here. The next bit is that we need to figure out the bounds. And so I think it's going to be useful to take these equations here and to put them into spherical, obviously, because we're supposed to be integrating with spherical. So let me go ahead and maybe take this one, for instance. And if I maybe square both sides and rearrange, we get that this is a sphere of radius 1. Right? According to our formula sheet, x squared plus y squared plus z squared is supposed to be equal to rho squared. Because we don't allow for negative r's or rho's in our class, when you take the square root, normally it's plus and minus, but we're going to only choose the positive one. So this is probably going to show up as a row bound somewhere. The other thing that we need here, a little bit more complicated, is our cone equation. And when I see this, and especially because we have this x squared plus y squared over here, I'm going to pit stop first into cylindrical. So I'd write this personally as, instead of x squared plus y squared, I would do r squared. And I'm going to go ahead and break up my square root. So I need to take the square root at the top and the bottom. I can do this one at a time. And then the square root of r squared, because, again, r's are only positive. Normally, this would be the absolute value of r. But because they're only positive, this is just going to simplify down to r. Now we're at least halfway there. But again, I need to get this into spherical. So into spherical, we can use that z is rho cosine phi, and r is rho sine phi. Now, so long as rho is not exclusively 0, it's certainly not in this case, we can divide by it. And we see that all we're left with is phis. So maybe we could try to solve this for phi equals. So if I was interested in trying to solve this phi equals, I'd probably rearrange it and divide by cosine of phi on both sides. Sine divided by cosine is tangent. Now, if you're good friends with the unit circle, you may be able to just look at this and say that phi is equal to pi over 3 and be good with that. However, I think there's many of us who have a hard time making such a jump. And so I would recommend, right, that you put the square root of 3 into your calculator, and you're going to get some decimals, right? And then you could also plug in the common values, right? Tangent of pi over 6 and tangent of pi over 4 and tangent of pi over 3, maybe to start. And you're going to notice that when you plug in tangent of pi over 3, you get the exact same decimals as you do for root 3, right? And so your phi value ought to be pi over 3. So this is, of course, a way to do it without having completely memorized your unit circle for tangent. All right, so I know that my bounds should probably have a pi over 3 somewhere in the phi bounds, and they should have a rho equals 1 somewhere in the rho bounds. But still, I'm kind of missing 4 bounds then, right? Because I know 2 of them probably, but I need 4 more. And so this is where having a good picture is really useful. I think this one's a little bit cluttered, so I'm going to kind of recreate this. If I was to do it personally, like, if this picture wasn't provided, maybe in like the RZ half plane. So let's get a little bit of practice with that again. So if I was to graph this green surface, this is saying that no matter what phi value you choose, we're always going to take 1 step away from the origin. So if I'm looking straight up, we're going to take 1 step away from the origin. If we look a little bit over here, again, 1 step away from the origin. A little bit over here, 1 step away from the origin. So again, kind of always going to be taking 1 step away from the origin. We should go back here and just recall this is the positive square root. It should have positive z's, and hence the hemisphere here. And so I'm not going to go into the negative z's. But this is what's going to create my hemisphere. And then the purple surface is given by a phi of pi over 3. So remember, phi comes off of the positive z-axis. So if I do pi over 3 or like 60 degrees, maybe that's something like this. And again, this one acts a little bit different than theta, right? Theta usually comes off of the horizontal axis, but phi comes off of the vertical axis, right? So that's a key difference here between theta and phi. And now as we go back and we read this, you have to be quite careful because there's like two regions that we could shade, right? So we could either shade this region here, or we could shade maybe this region here. And I've chosen my colors suggestively. The green one's the good one. Well, let's go ahead and back to the question and read this to hopefully verify that that's the case. So it says that we want the volume of the solid bounded below by the cone. So that means that the cone should be on the bottom and bounded above by the hemisphere. So I want the cone on the bottom and I want the hemisphere on the top. So hopefully you can agree that the purple line here, which is going to represent the cone, is on the bottom of the green region, and the hemisphere, that green line, is on top of the green region. So with this, for instance, I know that my phi bounds are going to range from 0 to pi over 3, right? Excuse me. As we go out here, right, our region exists between phi equals 0 and pi over 3. After that, we're no longer hitting our region. But if we had accidentally shaded in that red one instead, right, that means that pi over 3 would have been our lower bound. We would have gone to like pi equals 2 or something like that for our upper bound. So it's important to have the picture to see that, again, our phi values should be from 0 to pi over 3. Likewise, we can see from this picture that as soon as you're really even on the origin, certainly as you take a tiny step off, you're inside of the region and you exit through this hemisphere here, which had the equation rho equals 1. So I think our bounds here for rho ought to be 0 to 1. And then lastly, for our thetas, as we went through this entire problem, we saw that there weren't any restrictions on theta. Theta can really be anything that it wants to be. And so if I want to make sure that I get all of my points once, but no more than that, I'm going to allow theta to range from 0 to 2 pi. Of course, if I went from 0 to 4 pi, I'd count all my points twice, and I'd get double the volume. All right, so now we have the good setup here. And by the way, if we wanted to get the 3D picture, just as we did in the pre-class video, we could take this and rotate it around the z-axis. And so it's this like ice cream cone shape here that we're trying to find the volume of. So all that to say, in the original picture that was given to us, we'd want to shade like this stuff here. Okay, that's the setup. Question? So why is that one in? Yeah, so the question was, why does phi come off of the positive z-axis instead of like the positive x-axis or the positive y-axis or something like this? And you could create a different spherical coordinate system where it does come off of the positive x or the positive y-axis or something like this, and that would be completely legitimate. However, just the convention that our textbook has and many mathematical textbooks use is that phi comes off of the positive z-axis. So I'm sad. I don't have a better explanation than it's just the convention that the textbook has chosen. So I understand it's not super compelling. But someone's got to make a choice somewhere. So they chose Z instead of X or Y. All right, good. Well, let's go ahead and do the evaluation then. I noticed that all of my bounds are constants. And we could write this as a function of rhos times a function of phis times a function of thetas. So we can choose to go ahead and split this up. 0 to 2 pi of 1 d theta, integral of 0 to pi over 3 of sine of phi dphi, integral of 0 to 1 rho squared d rho. So rather than evaluating out each integral one by one, you can really do all three of them in one step. We saw plenty of times in the cylindrical class, right, that when you integrate one, you're going to get theta, and you evaluate that from 0 to 2 pi, you're just going to get 2 pi minus 0. So the theta integral is quite quick. When you integrate sine, you get negative cosine. We'll have to plug in the bounds here. And when you integrate rho squared, you get 1/3 rho cubed. Cosine of pi over 3 is 1/2, minus a negative, which should be plus, and cosine of 0 is 1. And so at the end of the day, I believe we get the answer of pi over 3. Again, it's asked us to find a volume. And this is true volume, by the way. This isn't like net volume or anything like this, where we count it negatively if it's below like the XY plane or something, right? This is true volume. And so you should always get a positive answer. And if you don't get a positive answer, I would be alarmed, right? Because you probably made a small mistake somewhere and plugging in your bounds or something like that. And so that's a good indication that you should go back and double check things. All right, any questions on this one here? Yeah. You would never see a negative volume.
Like, so I've seen in the Weber report that you like will integrate it's like net of 0, like no volume.
So if you're doing a double integral, in that case, right, if it's above the XY plane, you would get a positive answer. And if it's below the XY plane, because that Z is being counted negatively, then you would get a negative. So that would be like net volume in that case. So the double integral could end up yielding a negative result if you take it from the XY plane to some surface that's below it. But whenever you do a triple integral like this, you're always going to get a positive answer. So it sounds like maybe the situation that you crossed is where you had some double integral where half of it was above and half of it was below, right? And in that case, they would kind of cancel out in some way. There's also plenty of other things that triple integrals do than besides calculating volume, right? If I was to integrate, for instance, for this one here, if I just changed it and I said, I want you to integrate the function x, then I claim that half of the x values are positive and half the x values are negative, right? And so they will cancel out and this would yield 0. So there's plenty of other triple integrals that can yield 0 or negatives, but those aren't volume integrals. All right, good. Well, why don't we go ahead and try another one then? So this one hasn't said you have to use spherical, but it's been awfully suggestive because it's given all of our equations to us in spherical form. So again, if I saw this on a quiz or an exam or what have you, the first thing that I would do is recognize that it's asking for a volume. That's going to be the triple integral of 1. I'm going to convert this into spherical. And there's a bit of partial credit earned. The next step, the harder step, right, is figuring out all of the bounds. So now we really need to go in and start deciphering It talks about a sphere, and then it talks about a hemisphere. To get practice, it has asked us in this case to sketch some pictures. So let's go ahead and do that. This rho equals cosine phi is very analogous to what we did in the pre-class video. I think in the pre-class video, the only difference is there was a 2 here, right? But the same storyline is going to follow, without that 2 as well. And so what I'm going to do, and what we did in the pre-class video, right, is that we kind of choose a bunch of different phi values. So maybe phi equals 0 would be straight up. Phi equals pi over 6, pi over 4, pi over 3, pi over 2. And as we saw in the pre-class video, right, something happens when you start going down here. We can talk about that again. But here would be maybe phi equals 2 pi over 3, for instance. All right. So again, the formula is rho equals cosine phi. So if my phi is 0, aka I'm looking straight up in the direction of the positive z-axis, and I plug that in, I would get rho equals cosine 0. Cosine of 0 is 1, so this is giving me rho equals 1. So this tells me I need to take one step away from my origin. So my point would be maybe up here. When I look in maybe like the pi over 6 direction, I'm going to have rho equals cosine of pi over 6. And we plug this into our calculator. Maybe it's around like 1.7 divided by 2, so maybe like 0.85, a little bit less than 1. So I don't take a step quite as far out. Next up, I look in the pi over 4 direction. Cosine of pi over 4 is root 2 over 2. So root 2 is like 1.4. Divide that by 2, that's going to be around 0.7. So a little bit smaller still. Cosine of pi over 3, that's going to be 1/2, so 0.5. Cosine of pi over 2, that's going to be 0. So we start connecting all of these points here. Now, when you go beyond pi over 2, and for instance, if we tried to plug in 2 pi over 3, cosine of 2 pi over 3 is a negative answer, right? It's negative 1/2. And so this is a bit alarming because now we have rho equals negative 1/2. We've already said in this class, right, if you start having negative rows, you're going to be double counting points. So in particular, right, the rho equals negative 1/2 would be back here somewhere. And you would end up double counting this point if you were to include that. So that's how you know you should stop, right? Once you start getting negative rho values, an alarm bell should go off, right? You'd say, well, I probably shouldn't allow for that. And so we're going to stop at pi over 2. So our picture so far should look something like this. Again, very similar to what we had in the pre-class video. Now the next surface is rho equals 2. So notice that this doesn't really rely on what phi is. Phi could be 0, and this is saying go out 2. Phi could be pi over 6, and this is saying go out 2. It could be pi over 4 or pi over 3 or what have you, right? And all of this is saying rho equals 2, rho equals 2, rho equals 2. And so no matter what the phi value is, you always take 2 steps away from the origin. Now this one had to explicitly say that z should be greater than or equal to 0. So that's why I stopped there. So the region that's bounded between these two is going to be something like this. Now this has also asked us to take this and get a picture in the XYZ space. So why don't we do that really quick before starting to talk about our bounds. Oops. So if I take this purple sphere here, which just right now looks like a little half circle, and if I was to spin this around the z-axis, right, my claim is we get a sphere. And if we were to take our green curve here and spin this around the z-axis, we get this hemisphere. So the volume that we're trying to find is this here. Kind of looks like someone's taken half of a watermelon and scooped out some in a difficult way. Personally, when I am finding my bounds, I think it's easier to use the RZ half plane. And so I'm going to rely on this. I think just having this 2D picture is powerful enough. But we can also, talk about where these show up in the 3D picture as well. So if I was thinking, right, I'm traveling my row direction. It seems like I always enter in through this purple curve, and I always exit through this green curve. So my lower limit should be this rho equals cosine of phi. That was the purple curve's equation. And the green curve's equation was rho equals 2. That nice constant there. Now, for each of these curves here, and for their own separate reasons, we found that, well, yes, there's some of the surface and all that exists when phi equals 0, looking straight up. But then it stops at pi over 2, 90 degrees, right? And neither one has anything going on below here, and I guess like the fourth quadrant or something. So again, the reason why the purple curve stopped was because we started getting negative rho values. And the reason why the green curve stopped is because it was specified that z should be greater than or equal to 0. So each for their own reason, phi should only range from 0 to pi over 2 rather than 0 to pi, right? The default for phi is 0 to pi, unless there's some restriction like there is in this equation. And then finally, as we look through all of this, right, there were no restrictions on theta whatsoever. Theta was never even brought up. So if we want to get the entire thing here, theta should range from 0 to 2 pi. I've also seen plenty of problems out there. I know we've had 2 in a row now that are 0 to 2 pi for theta. That is common. Another common one that I sometimes see is it may have all of these same words here, but it may talk about the volume in the first octant, right? And so if you're restricting yourself to just the first octant, where x, y, and z are positive, what would your theta range be in that case? Wouldn't be 0 to 2 pi, would it? It'd be something else. What? 0 to pi over 2, exactly right. Yes. So yeah, 0 to pi over 2 if it said first octant. So that's another common one that sometimes comes up. All right, so I think we have the setup done. Again, I think this is the hard part. Next up is to evaluate. Question though, before we do that.
So for low bound, the lower bound is cosine.
Yeah, so for rho is this radius that comes from the origin in the RZ half plane. If you wanted to do this in the 3D picture, right, it's the 3D radius. So if I was to emanate out of the origin here, again, rho squared is x squared plus y squared plus z squared. So it's talking about how far have you gone from the origin. Again, it always seems like we are exiting, sorry, we're entering into our region through this purple sphere, and then we are exiting as we continue outward here through this green surface, this hemisphere. So it's a question of how do we enter into our region and how do we exit? That's going to be our lower bound and upper bound. Okay, when should we start shading? When should we stop? So the lower bound is when should we start shading? The upper bound is when should we stop shading? And so we hit the rho equals cosine phi, this purple sphere first. That's when we start shading. And then as we continue outward, we exit, we stop shading at rho equals 2. Did that help? Good. Okay, so let's go ahead and evaluate this one. I notice that there is a cosine of phi here. in our bounds, so we can't completely separate this out. But I at least notice that there aren't any thetas anywhere, right? There's no thetas in our integral. There's no thetas in any of the bounds. So we at very least could go ahead and evaluate out our theta integral, which is going to be the integral of 1 from 0 to 2 pi. Then we could evaluate out our rho integral, and at least then we'd get 2 and 1 here. So evaluate out my rho integral. Integrating rho squared is going to be 1/3 rho cubed. And I'm going to need to plug in these bounds here. I guess let's go ahead and bring out this 1/3 as well. 2 cubed is going to be 8. Cosine cubed is going to be, well, cosine cubed. Let's take one more line to simplify, and then we can do our final integral here. I mean, I can integrate cosine perfectly well. All right, we're going to have negative, sorry, I can integrate sine perfectly well, and we're going to have negative cosine here. Need to evaluate that from 0 to pi over 2. However, this second one is a little bit more complicated. It has sines and cosines and all that sort of stuff. What technique should we use in order to integrate that one? Yeah, u sub, right? So we're going to use a u sub, where u is equal to cosine. And then in that case, we're going to have du is going to be equal to negative sine of phi d phi. So I can trade in my negative, my sine, and my d phi, all of this sort of stuff for a du. And so this is just going to become the integral of u cubed du. So when I integrate that, I'm going to have 1/4 u to the 4th. And u again was cosine of phi. I still need to evaluate this from 0 to pi over 2. So cosine of pi over 2 is going to be 0, minus cosine of 0 is going to be 1. Cosine of pi over 2 is going to be 0. Raise that to the 4th power. That's still 0. Minus cosine of 0 is going to be 1. Raise that to the 4th power. You still get 1. So my final answer is going to be this 2 pi over 3 times 8 minus a 4th. Of course, we could simplify this more, but this is probably the point. If this is a Weber question, I'd just type this exactly into Weber. If this is a D2L quiz or exam question, this is what I type in my calculator and get some answer to 3 decimal places. All right, any questions on this one here? All right, well, I've been presenting a lot, so I'd like to give you guys an opportunity, maybe take 2 or 3 minutes. Oh, sorry, question, yeah. How did I get the cosine phi? For which part? The one next to the 8 or the one next to the 1/4? So I needed to integrate sine. So the integral of sine is negative cosine, right? Or likewise, if I take the derivative of negative cosine, I get positive sine. So that's how I got that one.
Can we filter out the sign entirely and like cross out the sign with the use of this?
You're asking if we could just leave it factored? Yeah, I mean, you could make this as 8 minus u cubed, and then all of that would be your du, something like that. That would be fine. All right, so yeah, please take 2 or 3 minutes, get as far as you can on this one. Volume of another solid bounded below by the sphere and above by the cone. As I walked around, I saw quite a few good pictures. Our sphere looks again. This 2 cosine phi. It's going to be very similar to our last one, but just scaled by a factor of 2. And then if you do the same sort of steps that we did a couple problems ago, our cone was actually more complicated back then. But when we did these steps of converting our cone maybe into cylindrical and then into spherical, and you play the same sort of game, this time you're going to have a 1 over here rather than a root 3. And so you're going to get that phi equals pi over 4 this time. Now, what I wanted to talk about was it's not clear from this picture maybe alone which region we should be shading. So I've shaded one here in blue and one here in purple. And I was wondering if anyone had maybe a compelling reason why we should choose one rather than the other. Yeah? You like purple, why? Good. So, I mean, it's really just about taking your time and reading the problem carefully. I understand on quizzes and exams, time's of the essence and you try to go fast, but you'll get the wrong answer if you set this up and try to find the blue region rather than the purple region. So again, solid is bounded below by the sphere, aka the sphere should be on the bottom of the region. It's bounded above by the cone. That means the cone should be on top of the region. So you're looking for the region where the cone is on top and the sphere is on bottom. That's the purple region. Okay. Beyond this, We're interested in volume. So similar to last time, we're going to have a function of 1, and then we convert it into spherical. I fear I won't have time to cover it in class, but the last problem here, as you look at this, here's one where it's not calculating out volume, right? But it's giving you a different function. However, this one would be quite fast again to convert into spherical. That's just rho squared. And so in that case, you'd have like rho to the 4th here rather than rho squared that you'd be integrating. So I don't feel like I've cheapened you, too much by choosing volume problems here for the first 3. All right, now for the bounds. As I travel outwards, aka in my rho direction, it seems like on the origin, I'm like on the boundary of my region. And as soon as I take the tiniest step off that, I'm inside of my region. So it seems like rho equals 0 is how I enter, and how I exit is through this purple curve. And luckily, this has a rho equals equation. So I think our bounds here are going to be from 0 to 2 cosine phi. Our phi values, aka where we're shading, they seem to be in this region right here. Again, phi comes off of the positive z-axis. So it seems like we start when we're at this green line here, which had a value of phi equals pi over 4. And we don't have any picture, down here in like the 4th quadrant or whatever this is, right? And so we're going to have bounds from pi over 4 to pi over 2 for phi. And then again, just like we've seen in the past couple, none of these have anything to do with theta. And so our theta bounds are going to range from 0 to 2 pi, since we want to get each point once, but not more than once. Any questions on the setup here? Yes. So pi over 4 to 0 would be like, so here is pi over 4. Oops. And here is 0. So it'd be like this. I guess first of all, it's a little bit strange because pi over 4, right, is some number around like 0.75 or something like this. It's a little bit strange to have your larger number on the bottom and then your smaller number on top. So that's kind of a bit alarming. But then, yeah, you'd be going from this bigger number to the smaller number. And again, we haven't really shaded anything in this region whatsoever. Good question, though. Guess that's key. Good. Any other questions? Yeah. Yep. Yeah, so I didn't go into details because I saw a few people had this quite well on their papers as I walked around. But the exact same steps that we do in order to solve the for the cone 2 times ago, right? You're going to get rho cosine phi equals rho sine phi, cancel out the rows, and you're going to look for a place where sine is equal to cosine, or equivalently where tangent is equal to 1. Either one of these will yield you the answer that phi should be pi over 4. All right, in the last 2 minutes, why don't we go ahead and try to solve this. Just as before, don't see any thetas in our bounds or in our integrand, the function that we're integrating. So I can evaluate that integral quite quickly. When I integrate rho, I'm going to have 1/3 rho cubed. This time I'm going to be evaluating from 0 to 2 cosine phi, though. And then I'll still have my phi integral. Just as before, I'll go ahead and factor out that 3 now. Plugging in 2 cosine phi in everywhere I see a rho, I'm going to get 8 cosine cubed phi minus 0, I suppose. I could bring out this 8 as well. And then just as before, if you do a u substitution with u is equal to cosine, then du is going to be equal to negative sine phi d phi. This time we don't have the negative sign, so I'm going to go ahead and write it that negative du is equal to sine phi d phi. So I'm going to trade in all of this stuff here for du, or I guess negative du. And then I'm just going to have the integral of u cubed negative du. So when I integrate that, I'm going to have 1/4, I guess negative 1/4 because of the negative du here. So negative 1/4, u to the fourth. U again was cosine. And we should plug in some bounds. I'm a little bit worried that we have a negative sign here. I hope that somehow goes away because again, we are calculating out volume. We should have a positive answer. So cosine of pi over 2 is 0. Raise that to the fourth power, it's still 0. Cosine of pi over 4 is root 2 over 2. Raise that to the fourth power. Well, we've got a little bit of work to do here. But at very least, I see we have these two negative signs, so those should nicely cancel out. I'm happy about that. We should get a positive answer here. Root 2 to the fourth power should be 4. So you take it and you square it, and you square it again. So when you square it the first time, you get rid of the square root. When you square it the second time, 2 becomes 4. Of course, your calculator can verify this for you. When you take 2 and you raise it to the fourth power, you get 16. So these two 4s will cancel out with our 16 here. And my answer happens to be pi over 3 again. All right, I apologize for going a bit over, but we were close to the end of this problem, so I thought we should finish. I invite you to look at this problem and try it on your own. I'll post the solutions to it on our D2L page by 4 o'clock today. Quite similar, but again, instead of integrating 1, we're integrating rho squared. So slightly different results, not all that different though. All right, I'll stick around if you have any one-on-one questions. Otherwise, have a great weekend, and I'll see you guys Monday.